Okay, thank you very much for giving me the opportunity. Thank you, Shuki, and everyone at Semi Israel for inviting me to come here today and talk about the lifetime prediction and qualification from MTOL and not HTOL. And well, actually, it's a lot of information to give in this short amount of time. So hopefully I'll be able to do justice to the topic. But we've actually been working on this for a long time. It's been at least 10 years in the development, and we actually have a few customers. And we'd like to present with you the problems with the current approach to doing reliability assessment. So basically, there are inherent problems with HTOL, and I'll bring those up. The high temperature operating lifetime test, which is this industry standard, and I'm going to say it's basically a pretty useless exercise. We're going to understand what happens when you have interactions of multiple failure mechanisms at the same time in any system, certainly in any electronic product, any chip even, or any system, or MEMS systems, or LEDs, or anything else. And I'm going to present to you this reliability matrix solution that we perform for you, and we do this as a service. And I'm trying to, I'll say, advertise the laboratory that we have, and our services could be very useful for industry in Israel. We have a few happy customers, and I'd like to increase that list. And I hope that you find this interesting. And I'll show you the MTL reliability prediction approach. We actually give lifetime predictions. We can evaluate the actual failure rate that you expect based on whatever operating conditions you give us. And of course, we know that prediction is very difficult, especially about the future. So how does it work? So basically, first, what is the failure rate? Failure rate is often described as what we call the lambda, which is a rate process. A lambda being a rate process means we choose a time interval, delta t, and we count the number of failures you expect, the number of failures n, and it ends up being, because we don't know, they're sort of random events and we don't know when they're going to happen exactly, so we have to give a probability on that number. So we say there is an n plus or minus square root of n over time. So in any lambda, there's an inherent uncertainty in the number that were found in the interval. So we take a time interval, count the number of failures within that interval, and delta n, that is to say n over delta t, is your rate. And you go along in time, and if you see the number per time increasing or decreasing, in this case it looks like it's decreasing, then you can say your failure rate is decreasing over time, and eventually you're going to have a lower failure rate than you did to start with. We call that process burn-in. But if we notice that the failure rate is approximately constant, then we say we have a constant failure rate, and that's a lambda, which is independent of time. The failure rate is independent of time, and that's by industry called the FIT, failure in time. So you get a standard deviation in n, of course, is sigma, and that is going to be plus or minus 1 over the square root of n minus 1, where n is the number of failures you found, which is the number of degrees of freedom you have in fitting this lambda function. So since there is only one parameter lambda fit with n points, n minus 1 is what gives you the number of degrees of freedom, and 1 over the number of degrees of freedom is your uncertainty in n. Okay, very simply, that means you have to assume some sort of a function, a probability function for your failure rate. So the reliability now is going to be 1 minus the probability of failure. So the reliability is the probability of 0 failures over time. So the reliability is e to the minus lambda t, where lambda is now the only parameter and is time independent. So the reliability is e to the minus failure rate times time. So the mean time to fail is 1 over lambda. So the mean time to fail is 1 over lambda, and it's a one-sided distribution. The variance on that is going to be plus or minus that same mean time to fail, and that's regardless of how many samples you've tested, because it is a Poisson process that's bounded on the left-hand side by 0, since you can't have anything fail before you start. And the standard deviation, of course, is 1 over the square root of 1 over lambda, square root of this time to fail. So lambda is constant, time independent, which means it's the same failure rate. Assumption is that it's the same failure rate from when you start as it is in the end. Now, in most of our cases, since we work with products that actually work, What happens if our failure rates are very rare? That is to say, the number of failures per hour or per day is very small, such that we can't actually tell the rate with any confidence. So really, if you want to have any confidence, let's say 95% confidence, you have to make sure you have a delta t, your interval has to be large enough so you expect to get 3 failures within that time. If you have, if your delta t is too short compared to the actual number of failures, you can get 0 or 1 or 2. And the fewer data points, of course, is your higher is your variability. So no failures actually is worse than no statistics. That's because you have that sigma over is the number of failures n minus 1. So the square root of n minus 1, if n is 0, the square root of -1 is an imaginary number. So there is no such a thing as a probability confidence level when you have 0 failures. Really, you need 3. 3 is the magic number to have any confidence on the rate function that you're measuring. And 0 failures gives no data for fit for a failure rate. So what do we do when we have 0 failures? Since companies are not allowed to show failures, all parts have to pass a final qualification by having 0 failures out of whatever number tested. So what do we do? Well, what the industry does is, I'm going to show, is not really a very sufficient solution from any intellectually honest process. We'll pick a number, any number close to 100, say maybe 77 parts from 3 lots, for example, operate them for a long time, maybe 1,000 hours, and to see that they all work. And then, of course, they all pass, so you have 0 failures, and then tell your customers you never accept failures. Okay, so here's the inconsistency with this high temperature operating life approach. HTOL, I'll say, is a very expensive and I'll say useless exercise, where you have the 231 parts tested for 1,000 hours, which is a lot of money on testing time, because if you spend, let's say, even, I don't know, $5, $10 an hour of parts, you're spending a lot of money, and you're getting 0 failures, so everything's great, and you have none. And if any of them failed, you're in trouble, so you're gonna have to do the system again, do the test again. And H2L assumes now this constant rate. And here's the problem, because you can only get a constant rate, we can show, if you have multiple failure mechanisms operating simultaneously. Well, there'll be interaction between them, and the failures in the end will become random, and they'll be Poisson distributed. However, the mathematics of the H2L assumes that there's only a single acceleration factor, which means only a single high temperature and, let's say, high voltage or high stress test is used to validate your devices. So it is only valid for accelerating a single mechanism. So you can't have it both ways. You can't both assume that it is a constant rate, which implies multiple mechanisms, and also use the acceleration factor for a single mechanism and then assume it is constant rate. You can't have both of these factors. So I'll try to explain this a little bit better. Let's say an industry standard fit is the number of failures over the number of parts tested over time times this acceleration factor times 10 to the 9. So you get parts per billion failures per billion part hours. And this acceleration factor is a product of the voltage and temperature acceleration generally. So you have some multiplication of the voltage and sometimes the temperature. The problem is that there are 3 problems. The acceleration factor actually does not fit with any known mechanism. If you look in what industry publishes, they make up some mechanism for which they don't even see in the industry, and it has a very high acceleration factor, of course, because if you make a very big number down here, this number becomes very small, and you can show your customers a very nice, reliable product without having any knowledge of what's going on. 2, when 0 failures are reported, there's no statistical meaning, as we said. So the fact is you're assuming one mechanism and you're assuming constant rate. And your third problem is that you have an uncertainty assumed for this 0 failures. So really, I'm going to try to show you a little bit more clearly that 77 parts times 3 lots times 1,000 hours, 0 failures has no statistical significance confidence level. So let's be honest. Why don't we just put 0 in the numerator? Okay, so the fit is 0 parts. No, because then you get 0 fit parts per billion, and you can't report 0. That would be too honest, because that's what you actually measured, because that your company allows you to do. So what we'll do is make up a new statistic that nobody understands and just let everybody accept it. Call it chi-square because it sounds complicated enough. And since nobody knows what that is anyway, usually people will nod their heads and say, okay, it sounds good to me. And here you can see in the JEDEC chi-square is their standard. They'll say the lambda, the failure rate, is this chi-square number in the numerator divided by 2 times the acceleration factor number tested times this time of the test. So n is the sample size, so 231, et cetera, et cetera. So what is this chi-square statistic that nobody knows? It's based on this desired confidence level, often 60%, which is not something that anyone would really accept. Since 60% is the confidence of the statistics, means it is just as likely to be correct as not correct. And then you have the second subscript d, which is the number of degrees of freedom, where they add 2 just so you don't get 0. It's really f minus 2 or f minus 1 if you have only one factor. So they say 2f plus 2, because this is a number that will give you a non-zero result for the numerator, the top part of that fit curve. So it's what you need to do. So these are for early life test failures, and they do this even for late end of life failures. Since you get 0 failures anyway, there's no upper confidence limit. So there's no equals, there's no lambda equals this. You want to say is less than or equal to, but that assumes that you're using a constant rate model. Okay, so here's the chi-square table that you're supposed to diligently look up. 0 failures gives you 2 degrees of freedom for some reason. And they will never justify this. So you divide it by 2 because that's what the formula says. Chi-square over 2 is the Poisson function for n. And if you look at what is chi-squared over 2, it does look pretty much like the Poisson function. 60% levels. If chi-squared is 1.83, divide by 2, you get something close to 1. If you have 1 failure, add 1 to it, you get 2. 2 failures, add 1 to it, you get 3. And go on. You can put any number you want in the top. But this is all based on this f plus 1 or 2f plus 2 in the numerator. Okay, so as I say, you should not try this experiment at home. Make sure you do it in a good laboratory, and make sure you have JEDEC standards behind you, because 1 is infinitely greater than 0. But using Poisson statistics, of course, a posteriori, which means after you've done the test and you didn't find any failures, you can say the probability of getting 0 and 1 are equally likely. So I'm allowed now to, instead of 0 on the numerator, put in a 1, and it seems like a legitimate use of 0 failures. I've done my job. But don't be fooled. The degrees of freedom are still negative. You can never have less degrees of freedom than you have data points. So we can only invoke this chi-square. We only invoke this chi-square when the number of failures, in fact, is 0. Because if you actually had failures to report, you would actually have statistical significance of your sigma. So manufacturers qualify parts they generally at 1 accelerated temperature and voltage, and any test can only accelerate 1 mechanism since you're only doing 1 test. And your acceptance criteria, of course, is 0 failures, so you could never even justify the fact that you had a failure or didn't have a failure. And of course, 0 failures, we say, is imaginary statistics with a reported 60% confidence. But we all know that sigma is the original statistical confidence over n minus 1. So this use of chi-square, by the way, is unique in microelectronics. Of course, it contradicts any books on statistics, and it contradicts reality. So the standards are just downright wrong. And it's really amazing to me that for the past 20 or more years, people continue to report 0 failures as if they have things to report. Now, if you have multiple mechanisms, of course, you certainly cannot simply combine multiple mechanisms into a single mechanism model because activation energies don't combine. And HTOL has no statistical validity if there is more than a single well-defined mechanism that is considered. And of course, if there is only one mechanism, then the Poisson statistic is simply not correct. You should use some sort of a Weibull or some distribution where it is not a constant rate, because generally single mechanisms will have a time to fail, which is what we found happens on almost any system which has a single mechanism. But of course, since success is the probability of 0 failures, the reliability is understood to be the sum of the reliability of each component, or the sum of the reliabilities of every failure mechanism. So the reliability in reality is the reliability of mechanism A times B times C times D. And since they're all nice Poisson exponential functions, I should be able to multiply these together, which means I would add up the lambdas. So the final lambda e to the minus lambda t is simply the sum of lambda A plus lambda B plus lambda C plus lambda D. That's very important. We're not multiplying lambdas. We actually have to add them, which means we have to consider each mechanism separately, since each factor adds to lambda. So in other words, if you have an activation in one process that has a very high activation energy, say 0.6 eV, another one even has a negative activation energy, like a hot carrier effect or some other type of stress-related fatigue effect, you cannot combine a increasing and a decreasing mechanism in the model because you add the lambdas, which means you have to have a separate consideration for mechanism 1 and a separate consideration for mechanism 2. So basically, the normal methodology is just make some average acceleration factor. But the trouble is you can't, because if one has a positive activation energy or one has a large activation energy, one is even smaller, then you can't possibly combine them into one temperature that's going to accelerate both mechanisms equally, or one voltage factor or some non-thermal factor. So normally the signal and mechanism approach is 1 over the mean time to fail, which is the lambda, is simply 1 over the mean time to fast at test times this acceleration factor, and that's in the denominator in the bottom. If you have multiple mechanisms, you'd have to say 1 over MTTF, which is the total lambda, is the sum of 1 over MTTF1 plus MTTF2 multiplied by the probability of mechanism 1 and mechanism 2. So therefore, the effective acceleration factor for multiple mechanisms is 1 over the probability function over mechanism 1 plus 1 over mechanism 2. So what's interesting is if you have one mechanism that's very, very dominant, very large, let's say 10 to the 10, another one that's very small, let's say 10, then of course, when you add a very small number with a very big number, it's the big number here, which becomes dominant because you're taking 1 over the large number of the smaller number. So therefore, the true acceleration factor is actually the one that has the least acceleration during the test, not the one that you're assuming, which has the higher acceleration factor. So this is really the main problem with the HTOL, is that you're not qualifying the acceleration factor properly. So basically, since we don't have so much time here, I can basically say that if you try to look at a single mechanism model using the same exact statistics, assuming an acceleration factor for temperature and acceleration factor for voltage, you can end up getting very nice small low fits because you're assuming a very large acceleration factor. But the reality is if you have two mechanisms, one that's accelerated, let's say with high acceleration factor and voltage, but very low in temperature, and a second mechanism is the opposite, and assume you have 50% one, 50% the other, you'll end up getting about 2 orders of magnitude higher than what you would have actually have gotten from the HTOL. Okay, so I'm going to show you my solution here. And of course, it's better to be vaguely right than exactly wrong, thanks to Carveth-Mead. And what we're going to say is we're going to use the frame methodology as we've developed at Ariel. Define and conduct a series of step stress sequence tests in order to know what are the parameters that matter. And this doesn't matter if it's electrical or mechanical or even light. And I'll show you we did work with LEDs. Conduct MTOL design of experiments. Short experiments, we don't need to do 1,000 hours, we can do 100-hour tests, and apply the MTOL inversion matrix, which means we take each mechanism separately. We're going to look at, let's say, an example we have here of time-dependent dielectric breakdown, hot carriers, electromigration, and we actually do tests at different temperatures and voltages and stresses in order to expose different mechanisms. The example we're showing here from electronics has oxide breakdown, bias temperature instability, but you can do the same thing with LEDs and other types of devices in order to expose different possible physics of failure mechanisms. And then we can actually build a matrix based on the physics of expected failure rates. And you can see actually that use conditions, you will always get a dominant mechanism that's different than what you get from HTOL. The HTOL says TDDB should be overwhelmingly large, but the fact is because it's overwhelmingly large at very high temperatures and voltages, at use conditions, it's practically non-existent. So you will always find that when you do accelerated testing, you're always accelerating the wrong mechanism. So we verified this with FPGAs and we built ring oscillators. You see the oscillator degradation, and from here, and we did the same thing with LEDs, I'll show you when we did with gallium nitride devices. you can actually see extrapolations to when would be the time to fail. You find the time to fail on each condition, and then from there you can build the matrix, and you'll actually get a fit prediction. You can actually get the failure rate expected as a function of temperature, as a function of different voltages, and as a function of even frequencies or whatever different stressors you're using. So really, this is better than any reliability prediction tool. There's no handbook that can calculate the effects of multiple mechanisms simultaneously. Incorrect reliability information, of course, makes system engineering independent of goals, and that's not good. So reliability must fit your engineering goals. So we did this with gallium nitride devices. You can actually see the frequencies degrading, which means the RDS(on) increasing over time, and you can extrapolate to a time to fail. Now, as I said, we have a few customers. I'd be happy to have you be in touch with my friends at Camtech, and Maradin still use our services. They do micro MEMS, we do LEDs, and of course, we've done work with SanDisk on accelerated testing using the microelectronics. I'd like your company to be next, so please come give me a call, send me an email, and I'll be happy to work with you, and we can make a specified intelligent reliability test. We offer reliability predictions based on a linear combination of multiple mechanisms. Our model is based on data, not zero failures, and we actually extrapolate times to fail. And also, we cost a lot less than a standard HTOL, since we're not testing for hundreds of parts per 1,000 hours. We get away literally with 4, 6, maybe 12 parts, I guess more than 6 per each lot. And we test them for maybe a couple of 100 hours, 100 or 200 hours each. And we actually get very useful predictions of times to fail, and we can actually give you failure rate predictions too. And if there's a single mechanism, we can even give you Weibull curves, and we give you everything we need. So the result is you should do MTOL, not HTOL, and I thank you for your attention and all your time.